All right, so today we're going to move on with Unit 1, Lesson 1, which is all on functions. It's everything and anything you want to know about functions, from notation to graphing functions to inverse functions, composite functions, tons and tons of functions. Yesterday we did a real quick warm-up, and we talked about examples of functions that you should have had in your head, just random association of the word. We also talked about the formal definition. We filled this into our notes, and we basically used the example of dating where X's were the girls and Y's were the boys. When it comes to being a functional relationship, basically we discovered that boys are allowed to be cheaters, girls are not. Okay, that's really what we mean by function, aside from the one-to-one sets that are clearly just matched pairs. Okay, you have this information in your notes. Now, this is where we stop. To determine if y is a function of x. So you're going to be asked, please determine if y is a function of x. The first thing you do is you're going to solve your equation for y. You're going to graph it and see if it passes the vertical line test. That was something I was surprised nobody mentioned yesterday, was this concept of vertical line test. Usually functions, vertical line test exists. You could have written it down.
We kept going, and I was like, okay.
You were getting there. So, for example, example 1, solve the equation for y. Open up your graphing calculator, put that in for y1. Something like this. Okay, so when it looks something like that, we then use an ultimate vertical line, and we start and we drag it through the graph, and we say at any point in time, does the vertical line touch the actual graph shape at more than one location? And the answer is no, which means this in fact is a function. All right, so that's the first part. Now, example 2. Do you recognize what type of shape example 2 is? Do you recognize that equation? Why do you say parabola? Squared, x squared. So typically our definition is that x squared would indicate parabola because of the highest power of x. But there's actually a part B to that definition. And that's the fact that we're always in y equals x squared world. Instead of y equals, I have y squared. Shape. It is a circle. All right. So now, without even graphing this equation, do you know whether or not a circle would ever pass the vertical line test? No. So if you identify the type of equation it is, that may help you in answering the question that's being asked. However, I do want to show you this math because you're going to need this moving forward. If we wanted to graph this in the graphing calculator to solve for y, this is what our answer would look like. How did we get that? Well, we moved the x squared to the other side. So we've got 3 minus x squared. And then we took the square root of both sides. But if you remember, we've talked about the fundamental theorem of algebra, which says the highest power is going to indicate how many solutions that we have. If I have y squared, when I take the square root of it, I'm going to have 2 solutions, plus and minus. Okay? It's that same idea that you had learned about, like x squared equals 9. You take the square root of both sides. The answer is plus and minus 3, because x squared has 2 solutions. It's in that same vein. Please don't forget the plus or minus. That's where we get this. If you were using a graphing calculator to graph this, we would simply say that y1 was equal to the positive form of 3 minus x squared, and y2 is equal to the negative form of 3 minus x squared. It would actually graph the circle in two semicircles, top half and bottom half. Okay? You then look at the entire picture that's drawn in order to indicate whether it is or is not a function. Second part of this functions lesson has to do with notation. And this is one that I'm really going to stress with you because when you get to calculus, most of the functions that you're going to deal with, most of the equations will utilize function notation. F of x, for example. So if you take a look, what I think is in your notes is what it says. F of x means the value of the function f at x. This is how I would like you to think about function notation. Okay? So if I'm over here and I have f of x, I want you to think of f, the letter out front, as the name of the function. So when we say in terms of x, x is the input value. So what you're going to feed into the function are going to be the x values. What you're going to get out of the function is going to be the y values. And that also follows with what we always talked about with a chart. X, Y. What we're going to move to now, though, is that y is what you think of as the output. That's now going to be written as f of x, which seems very formal. But it's a unit that involves the name of the function and the input value to represent the output. So if you take a look at the first example, I have the function f, which will be in terms of x. That is 2x squared plus 4. You are asked to evaluate, find the value of f of 2. So notice that the 2 replaced the x. So when I go to my function up here, I go to the f function, every place I have an x, I substitute for the number 2. I then simplify using PEMDAS, which is why we did that earlier in the prerequisite, and I came up with an answer of 12. So what I want to show you, though, is that this could be asked numerous ways, especially on SATs. I could say something like, okay, when this is my chart, when x is 2, y is going to be 12. So this is my x value, this is my f of x value. It also means that 212 is a point on this function. All of those things are kind of synonymous ideas written in different math language. Now, if I look at example B, I'm going to go to the f function. Don't be weirded out. And rather than having an x, I'm going to replace it with a plus 2. So every place up here that I have an x, I'm going to take it out and I'm going to replace it with a plus 2. Notice, put the a plus 2 in. Following what we did using PEMDAS, we have to take care of our exponents first. That would be your FOIL situation, or distributing. Remember, the 2 doesn't go to both of them. It's like a times b times c. I then FOIL this, multiply everything by 2, bring the 4 down, and combine like terms to get my final answer. Now, if this looks weird to you, get used to it, because we're going to live here all the time now. This isn't the C harder problem, this is the norm now. Welcome to Algebra 3.
Would you write your answer like f for b? Would you write f and then in the parentheses put a plus 2 equals the answer we just got?
Like that?
Yeah.
Yes. So again, if we had a symbolic form of this over here with your x and your f of x, you would say that this would be a plus 2, And your final answer would be the 2a squared plus 8a plus 12. Questions? All right, let's move on to my favorite topic. How many of you, let's do a quick show of hands. How many of you dislike piecewise functions? Raise your hand nice and high, really high. This is going to be a large number of you. Be honest, it's okay. All right, the reason you dislike piecewise functions, in my opinion, is this. Number one, they look really hard. There's a lot of information in them. But number two, it's because you are used to reading math from left to right. Piecewise functions, you have to start on the right and work your way back. So what I'm saying here is that what's over here is always going to be your restrictions. So you have to start over here to figure out which line you should be on. Okay? So for example, you're asked to find g of 2 minus g of negative 8. So if I look at the number 2, which one of the restrictions becomes true when I plug in the 2? 2 is greater than 1 or less than or equal to 1? Greater than 1. So if I put the 2 here, this becomes true, which means this is the only line of the piecewise function that I need to use. So I'm going to evaluate g of 2 by plugging it into here. Now what about if I wanted to evaluate g of negative 8? Let me switch to red here. Negative 8 obviously is going to make this one true. So I'm going to use this function right here. Now, one more piece of advice for you. Whenever you're dealing with function notation, we talked about g being the name of the function, this being our input value. How many substitutions am I going to have? Well, technically, I'm going to have g of 2 being substituted, and I'm going to be g of 8 being substituted. What's the ultimate sign between those two functions? Got it. What's the ultimate sign between those two functions? Add, subtract, multiply, or divide. Subtract. Okay? So, when I go to do the problem, all right, so go to the g function, plug in 2. That means I'm going to plug it into here. Go to the g function, plug in negative 8, plug it into here. This is what it looks like in pure form. Okay, take a second to write all of that down with all of those parentheses. I know some of you do this in your head, but if you rely on your calculator for PEMDAS, you need to use parentheses to get the correct answer. So again, here is my purple part, and then here is my red part.
Mhm.
2 squared is 4. Please note that this subtraction sign right here is the same as this subtraction sign. On the inside of the red, I get a 64 plus a 24. That's where I got the 88 from. 4 minus 88 is negative 84. And I'm done. Questions on that? All right. The last thing that we're going to do is to talk about domain. Where have you heard domain before? Domain. Domain and range. Domain is usually associated with which variable? X. Okay? X in our table is what we're calling the input value. X is going to be your input. Here's the deal. Do you remember when we did the prerequisite, there were problems like 4 over x minus 1, and we would say, what are the restrictions on x? What would you tell me that x could never be here? Correct. You can't divide by 0. We talked about restrictions on what the variables are allowed to be. Well, if I'm restricting x, that means I'm restricting the domain. Right? So if we're restricting the domain, I want you to tell me what x is always allowed to be. So rather than stating the restrictions, x can't be 1, I would say that x is allowed to be every number except for 1. Right? There are 2 rules for domain that you have to look for. They are not going to change until we get to logarithms, and then we're going to add a third. The first one, you are never ever allowed to divide by 0. Never ever ever are you allowed to divide by 0. And the second one is that we are not allowed to take the square root of a negative number. Okay, so I understand you learned about imaginaries, but for instance, the square root of negative 9 technically has no real solution. So if it has no real solution, it can't be graphed in the coordinate plane using the traditional x and y values. Again, these are the only 2 rules. I'm going to stand up here and say, what are the 2 considerations for a domain? Can't divide by 0, can't have a negative underneath the root. Fantastic. So let's look at these last 4 equations in our notes today. Okay, first one, f of x equals x squared. Okay, so I'm going to focus on this. First question, do I have a denominator? No. Do I have a square root? Do you see a root symbol? Here? No. Therefore, I have no restrictions on domain. X can be any number in the world. My domain is going to be written using interval notation. It says it's from negative infinity to infinity. Here's infinity. Here's negative infinity. This is what my number line answer would look like. You should have transitioned last year from number line answers into interval notation. If you missed that, didn't have it, moved up from CP, you're going to need to see me because we use interval notation for our solutions for domain. All right, letter B. Do I have a denominator? Yes. Okay, so when I look at letter B, here I have a denominator, which now employs the rule I cannot divide by 0. What is the only value that x cannot be? 1. So over here on my number line now, at 1, I have an open circle because I can never ever use 1. It will violate the denominator, which means I can use every number to the left, every number to the right, and we write that in 2 parts. We describe the left part of the number line from negative infinity to 1. We use a parenthesis because it is an open circle. Then we use this symbol which means union, or add to that another part, and we use from 1 to infinity, meaning we start on the other side. So if you have a denominator, most likely your answer will be in a format like this, where you have separate regions of the number line, separated using the union symbol. All right, letter C. Do I have a denominator? No. Do I have a square root? Yes. All right. Here's the rule for square root. I'm going to go to green for this one. Okay? Your rule for square root says what's underneath the root, x plus 5, must be positive, correct? Translated in algebra language, greater than or equal to 0. That's what you have to write down. How do I solve that linear inequality? How do I get x by itself? Bring the 5 over. X has to be greater than or equal to negative 5. On my number line, that's going to look like a solid circle shaded to the right. That gives me one region based on this inequality. We chose an inequality because it was a square root. From here, I can write my answer. Notice that now I have a solid dot, which means I have to use a bracket, not a parenthesis. then lastly, letter D. Do I have a denominator? Yes. What does the denominator tell me out of all the numbers in the world? X cannot be 1. Okay, so I'm going to draw this down here. Out of all the numbers in the world, file away the fact that at 1, I'm going to have an open circle. But do I have a square root also? Yes. So since we just did this in the previous problem, we know that x has to be what? Greater than or equal to -5. So now I come over here to -5, and I make a dot, and I shade. Uh-oh, I still can't use 1, even though I can use it in the top because it will violate the bottom. So I skip over that. In doing this, it creates two separate regions of solutions, from -5 to 1, and then from 1 to infinity. Notice my answer has that similar bracket for the -5, but then there is a break in the graph at 1, which we can see because we use parentheses. Right there. The infinities are always parenthesed, as a review in case you forgot that. We are done. You have the first assignment, number 6. Okay. Number 6.